System. Okay, so if you can imagine that first order neuron sitting out here for DCML, it comes in and then goes right up those columns, same side. We'll talk more about that as time goes on, but that's the gist of it. Now the other one that we talked about, or the other group that we talked about, were the dorsal and ventral spinocerebellar tracts. Okay, these are all somatosensory information, or sensory information coming in, afferent information. So here, more dorsal is going to be your dorsal spinocerebellar tract. There's one on both sides. Okay, so this is your dorsal spinocerebellar tract. Okay, remember that one's going to carry your non-conscious proprioception straight up to your cerebellum. We'll talk about that later on in the semester. And then just ventral to the dorsal spinocerebellar tract is going to be your ventral spinocerebellar tract. Cerebellar. This is your one on both sides. That's your ventral spinocerebellar. This top one is your dorsal spinocerebellar. Spinocerebellar. We talked about it in the very first drawing, the dorsal spinocerebellar tract. You don't have to fuss too much about what it's there for yet. We'll talk about it later in the semester. But overall, these carry the non-conscious proprioception. Both the dorsal and the spinocerebellar tracts, they carry your non-conscious proprioception directly up to the spinal cord. Bless you. We'll talk about that more when we get to the spinal cord portion of the course. The cerebellar portion of the course. Okay, and the last tract that we need to talk about is our old friend STT. And sometimes you hear STT called the anterolateral spinal thalamic tract because it exists here both in the lateral column and crosses over into the anterior column. So this is STT, or anterolateral spinal thalamic tract. You may hear that in your future. Okay. So it's both in the anterior and the lateral column system. And this is your STT. Yes?
You were repeating that one more time.
Anterior spinal thalamic tract. Anterolateral. Sometimes you might, I won't call it that, but you may hear in your future anterolateral spinal thalamic tract. And I'll write it down. And the reason is because it's crossing over from the anterior column system to the lateral column system. So that's anterolateral. So and it's called that because it crosses over into the two different columns. Anterolateral. Questions? Any other questions? Okay, that's it for the somatosensory information on the bottom. That's enough, right? Those are all the things that we talked about somatosensory-wise when we talked through that first picture. And now let's move up to the motor and just draw the important motor pieces that you need to be aware of. Here in the lateral column system is the big one. Bilaterally, you're going to have your lateral corticospinal tract. Okay, this is going to be that main tract that carries motor information from the precentral gyrus. And it's in your lateral column, so it's the lateral corticospinal tract. first one we talked about. Remember, from the level of the precentral gyrus all the way down through the spinal cord. That's going to be your big one, your lateral corticospinal tract. Okay, moving on down, thinking about the information coming from the level of the red nucleus down the spinal cord. Just underneath your lateral corticospinal tract, you have this tract, same color as before. This is going to be your rubrospinal tract. We also have to talk about, so in addition to the lateral corticospinal tract, there's going to be a small piece of the corticospinal tract that doesn't decussate. We'll talk about that before. But it travels through and it lives here in the anterior column system. So this is your anterior corticospinal tract. Okay, that's your anterior corticospinal tract. And down here, also in the anterior column system. And I remember this one's on the bottom because it begins with a V. Okay, it's most ventral. Right? Since it's most ventral, the other tract we talked about begins with a V is going to be your vestibulospinal tract. So here's your vestibulospinal tract. They're in orange. Tried to keep my colors consistent, so when you go back to the first, you can see it. Then there's only one more that we haven't talked about yet. I think I did that. Not colored. I'm going to make it brown. Right above your vestibulospinal tract, the only one that we haven't talked about yet is motor information coming down is going to be your reticulospinal tract. And that's going to be right under this, right over top of vestibular, or more just dorsal to vestibulospinal. And this is going to be reticulospinal tract. Okay, and those are all the things that we talked about in the first slide. Okay, this is nothing more than looking at where those tracts or vesiculi live in three-dimensional space in the spinal cord. Okay, nothing more than white matter axons traveling down the spinal cord, both somatosensory and motor information. Paul?
Don't they cross at one point though? So where has that work?
We'll get there. So the decussations is what you're talking about? Yeah, we'll see that. This is just flat out knowledge. You need to know what area of the spinal cord these things live in. Okay? Just basic mapping it out. Any other questions? Okay, let's move on. Let's move on to roots, nerves, and rami. This is a simple one. Have you guys covered any of this? Roots, nerves, and rami yet? Roots, nerves, and rami?
We talked about what a rami is.
Okay.
Spinal nerves and rami.
Okay. Well, we're going to see if we can add a little bit to that. So this is the...
Dr. Harlow, I'm sure we'd have multiple volunteers who could come up and draw the lumbosacral plexus for you.
Oh, that'd be great. I'm not going to... Come on up, Dr. Blair. No. Okay, so roots, nerves, and rami, this is relatively simple. Again, this is going to be my transverse section through the spinal cord. Remember that? So if we had to go through and label, this is the dorsal gray horn. Okay, and this is going to be your ventral gray horn. Okay, and it exists bilaterally. And if I told you that this structure right here is coming off the dorsal gray horn is where the first order neuron for the somatosensory neuron lives. Does anybody remember what this thing would be called? Yeah, that's my dorsal root ganglia. Okay. And then over here, you see it, on the right-hand side, these are my renditions of muscles. Okay, this one up here on the top represents back muscles. Okay. Okay. And we're also going to talk about, now that's a back muscle, and you're also going to have coming up to the back is back cutaneous sensation. So any somatosensation coming from the back. Okay, and then down here, up here, it's going to be dorsal musculature. This is going to be extremity and rest of trunk musculature. So this is extremity and trunk, excluding the back. Okay, and cutaneous sensation for these as well. Okay, now we're just going to look at how this information gets to the spinal cord and gets back out. So, dorsal root ganglia, you have your pseudo-unipolar neuronal cell body. Comes off a little stalk. Okay, and then that information is going to come in to the dorsal gray horn. And depending on whether you're SCT or DCML, you may synapse or you may go straight up, but for our purposes, that's somatosensory information coming in. Okay, and as I mentioned previously, the ventral gray horn is the location where these lower motor neuron or alpha motor neurons reside. Okay, so this is going to be your alpha motor neuron. Also call it your lower motor neuron. Any way you want to think about it, it's both the same. Okay. Your alpha motor neuron sends out motor information to innervate skeletal muscles.
What's the blue one?
The blue one is a somatosensory information coming in. So any general somatosensory, could be SCT, could be DCML, nothing specific. Just general somatosensory information coming in. Okay. Sensory information coming in. Now, out of the ventral gray horn, out of this alpha motor neuron, axons come out and they travel through this structure here. Okay. And then the dendrites coming from the pseudounipolar neuron traveling through here. So this is the dorsal root ganglia. This whole area here is known as your dorsal root. Bless you. This is your dorsal root. Okay, and then this down here is just your ventral root. Okay, so traveling out of the spinal cord proper, you have your dorsal root. Has somatosensory information. Yes, Paul?
Does it travel from both ways from the dorsal root ganglia, like both directions, or is it going like?
Okay, so the neuronal cell body exists here. Axons from here are going toward the spinal cord, and these are going to be the dendrites. We're going to make that connection here in a minute, if that makes sense. So it's not going to go to the ventral root. Only somatosensory information is going to exist in the dorsal root, and only motor information exists in the ventral root. That's an important point. That makes sense to everybody? See, the blue is all somatosensory information. Okay, now when you come through your dorsal root, somatosensory, this is the dendrite coming through. It's going to travel through here. Okay, and your motor information is also going to travel through that same structure. That's going to be your nerve. Okay, that's your spinal nerve. So spinal nerve carries a mix of motor and somatosensory information. Okay, so it's the dendrite coming from somatosensory and the axon from the motor. Okay, if there's information that is supposed to innervate back muscles, so we're talking about motor, this is information that's going to innervate back muscles, it's going to travel through this structure here. Okay, that structure is known as the dorsal ramus. Similarly, if there's sensory information coming from back musculature or the area of the back, cutaneous sensation, then those dendrites are going to travel through the dorsal ramus. Should be pretty straightforward. And then if there's information that's destined to innervate, motor information coming through, destined to innervate extremity and trunk muscles, it's going to travel through this structure, and that structure is your ventral ramus. And similarly, dendrites containing information coming, cutaneous sensory information coming from extremity and trunk are going to travel through the ventral ramus. Just that simple. Just looking at the two different systems. So once you get to the spinal nerve, you have a mixed bunch of information. Once you get to the dorsal ramus, you're thinking back. Once you get to the ventral ramus, then you're thinking trunk, rest of the trunk and extremity musculature traveling through the ventral ramus. Hopefully that's Sydney.
Is that upper and lower?
Upper and lower. Yes. I'm sorry, would it technically be what? Yes, it's on the other side, yes. I'm trying to keep my drawing simple. Ask me questions like that. So just try to make it super simple. So the point here is you guys should know what the root is. Here are the ventral root and the dorsal root. Dorsal root only carries somatosensory information. Ventral root only carries motor information. Spinal nerve is a mixed bag. Okay, dorsal ramus carries motor and sensory information destined for back. Ventral root carries motor and sensory information destined for trunk and extremities. Yes, Ben?
Is there a name for where the spinal nerve splits into the dorsal and ventral ramai?
So I don't know. Is there? No.
It happens like right at the intervertebral foramen, but there's no name for the split.
Yeah, not that I've ever heard of. Thank you for that. Yes, Jonathan. Johnny.
So you said the dorsal root carries only sensory information.
Correct.
And the ventral root carries only motor information.
That's correct. So see, all the blue is in the dorsal root, and all the red, which is the motor, is in the ventral root. Only the root carries ventral root, motor, dorsal root, somatosensory. Yeah, Mikey?
How do some of the sensory nerves in the extremities and the legs travel? It's just motor functions coming down through the ventral ramai. You know how like the ventral...
No, this is also somatosensory information. So the somatosensory information comes in through the ventral ramus.
Oh, I see. Okay.
Yeah. So I tried to say somatosensory would represent blue and motor is red.
I see.
So yes. Trace?
Is it equally split? Like, is the motor neuron and the spinal information equally split between dorsal and ventral ramus, or do they tend to go to one side more than the other?
It goes to the side of where it's going to innervate or receive information from. So if it's coming from the back, if it's motor information coming from the back, or motor information, not sensory information coming from the back, or motor information going to the back, it's going to go to the dorsal ramus. Yes, Alicia.
So how do you translate since all the tracks are in the white?
The tracks are only, this is all outside of that. This is more going to be the, I said the word well, but this is going to be the peripheral nervous system. But the tracks are all central nervous system.
So to clarify.
Clarify.
Okay. Dorsal ramus is to and from the back.
Right.
Ventral ramus to and from limbs and trunk.
Oh, that's the trunk.
Okay. And then the dorsal root is only sensory, ventral root is only motor.
Right. Yeah, just that simple. Should be pretty straightforward. Okay, so just getting some general concepts that we'll work through as time goes on. Okay, moving on. Doing good. All right. Let's move on to reflexes. We will learn how to do reflexes in this class. Yay. And that's going to be in 2 class periods. So we'll talk about your basic reflexes. Okay. Probably the most basic reflex, this is the reflex we're going to learn to do, is going to be what's called your myotatic reflex. It's also known as your stretch reflex. And you'll see why. Okay, thinking about, this is my basic cross section here through the spinal cord. All right, if I had to label this would be my dorsal root ganglia. Okay, this would be my dorsal gray horn, my ventral gray horn. Overall. And then I'm also going to have over here on your left, this is my representation of a leg. So these are hamstrings back here, and these are quads, and this is a femur in the middle. I put that in. Okay, hamstrings, quads, and femur. So these things that I've drawn in here, the brown that represent the muscle fibers, those are extrafusal fibers, and they're nothing more than muscle fibers, skeletal muscle fibers. How to feel? And this is a foot. We got it? Questions about how I set it up? I'm just looking at the body's response, and this is what's happening at the level of the spinal cord. And your myotatic reflex is just your basic stretch reflex. All you're going to do is a simple tendon tap, and by doing that tendon tap, the tendon is going to detect the stretch, or something specific in the tendon is going to detect the muscle stretch. Does anybody know what that thing is called? Muscle spindles. Okay, so put that up here. So there's also something, in addition to the extrafusal, which is the skeletal muscle fibers, running parallel to these skeletal muscle fibers, also existing in all muscles, there are going to be intrafusal fibers. And those intrafusal fibers are muscle spindles. It's just a sensory receptor that detects muscle stretch. So if we put our pseudo-unipolar cell body in the dorsal root ganglia. Okay, this is going to be a special kind of fiber that is hooked up with my intrafusal fiber. It's called a type 1A fiber. Type 1A fiber is there to detect sensory information coming from your muscle spindle, and your muscle spindle is there to detect stretch on the muscle. So if you take a hammer, or a reflex hammer, and you do a tendon tap on the patellar tendon, that intrafusal fiber, or the muscle spindle, detects the muscle stretch. It's got to be a quick stretch. It's going to be important when you learn how to do reflexes. It's got to be kind of quick. It's got to make it bounce. Okay? That information is transmitted through type 1A fibers all the way back to your spinal cord at the level of the dorsal, so through the dorsal root ganglia, the first order neuron is, and then it comes back, and then it's going to come in here through the dorsal gray horn, and at that point it's going to bifurcate. One is going to be, one of the axons is going to synapse directly with the alpha motor neuron, with an alpha motor neuron, and the other is going to synapse with an interneuron. We talked about an interneuron briefly when we talked about neuronal histology. Do you remember the interneurons, interconnector neurons in the spinal cord? So you're going to have one of the axons, it bifurcates, one's going to connect up with an alpha motor neuron, another's going to connect up with an interneuron, and that interneuron is specifically going to be an inhibitory interneuron. So I'll represent that as a minus sign, and that's hooked up with another alpha motor neuron, the lower motor neuron. Okay, so the direct tendon tap is going to be stimulatory to one directly, one set of muscles, either the quads or the hamstrings directly, and it's going to be inhibitory to the other set, to the antagonist. So when you do a tendon tap, what do you expect to happen? Knee what? Extension. Correct. So you're going to get knee extension, and that's going to activate what muscle? Quad. Yeah. So this is going to be the alpha motor neuron or lower motor neuron for quad muscles. Okay. And then if your quad muscles kick out and get activated, we can make that happen this way. So you're going to activate your quads, so you're going to get knee extension. Okay, if you get knee extension, what do you want to have happen to your hamstrings? What has to happen if you get knee extension? Sorry? They relax. They have to relax. Yeah, the hamstrings are inhibited. So if the quads are activated as the agonist, the antagonist has to be inhibited. And that's what happens here. So with the setup, we get the interneuron inhibiting the hamstrings. So this alpha motor neuron, this is going to be alpha motor for hamstrings. Because if your knee extends, if your hamstrings were active at the same time, you wouldn't be able to see knee extension, right? So you get, in order to get knee extension, you have to have the knee flexors inhibited. Does that make sense? Okay, so that process of activation of the agonist and inhibition of the antagonist just with a simple tendon tap is known as reciprocal inhibition. Okay, and that means nothing more than the agonist is activated and the antagonist is inhibited in order to see the muscle action of the agonist. Question? Reciprocal inhibition. Okay, so a tendon tap is your basic, there also you'll hear DTRs, deep tendon reflexes. That's all this is. This is your basic stretch reflex, your myotatic reflex. Another important thing to realize is that the myotatic reflex happens at the level of the spinal cord, right? There's no cortical information here. It doesn't have to go up to the level of the brain and travel all the way back down like these other somatosensory things we talked about, right? Everything's happening here, so it's really fast. No conscious thought involved, just relies on your spinal cord. Tendon tap and boom, you kick out. So it's a basic stretch reflex. It's known as a DTR, deep tendon reflex. Questions? Okay, basic DTR. Moving on. Let's look at the inverse myotatic reflex. So that's the myotatic reflex. This is the inverse myotatic reflex. Okay, kind of the same setup as before. I've got my spinal cord cross section here, transverse section, and then this is my leg muscle with the quads in the front, hamstrings in the back, and the femur. And when I first started teaching this course, I was thinking 50-pound weight for a single leg extension would be a lot of weight, and then I met a lot of guys that were coming through the program, and they recommended that I make this a 450. Okay, just to indicate that that's a lot of weight to lift. Okay, for me, 50-pound quad extension, that I could do that, but 450 is going to be super heavy. That's the point of this. Okay. In the inverse myotatic reflex, where the myotatic reflex works through muscle spindles, this is going to work through something known as the GTO. Does anybody know what GTO stands for? Yay! Heard of that one. Awesome. This is going to be your Golgi tendon organ. It's going to work through your Golgi tendon organ. Okay. Now, with your Golgi tendon organ, that is going to detect muscle tension. Okay. Where the muscle spindle detects stretch, or rapid stretch, or quick stretch, the GTO is going to detect muscle tension. Okay. And again, acts at the level of the spinal cord. So what we have here is, here's my neural cell body, dorsal root ganglia. Okay, I'm going to come out and specifically the tendon. So these are all going to be in the tendon of the muscle, okay, your GTO. If I tried to do a knee extension here, these dendrites are going to hook up with this GTO. Okay, receive information coming from the GTO. I'll label that as my GTO. Okay, detecting a whole bunch of muscle tension on those quad muscles. That's way too much to lift. All right, and GTO works through something called a type 1B fiber. Information is transmitted through here. Again, I have a bifurcation of the axons, and we're going to hook up with interneurons, and these interneurons are going to be hooked or linked synapse with alpha motor neurons for quads and hamstrings. And I'll keep the same basic position. So this is going to be quad and hamstring. quad alpha motor and hamstring alpha motor. Okay, but what I didn't put in is what these inner neurons are going to do when they're interacting. So, do you think if you're lifting way too heavy a weight and it's going to cause a problem, do you think that you want those quads to be activated or inhibited? Inhibited, yeah. So this is going to be an inhibitory interneuron interacting with the quads, and the interneuron interacting with the hamstrings is going to be stimulatory. So what you have is, in the case of inverse myotatic reflex, you have an inhibition of the quadriceps muscle to prevent it from ripping, and you're going to have an activation of the hamstring muscle. Where the muscle stimulus are detecting the stretch, too much stretch, especially quick stretch, could possibly tear the muscle. So it's a protective mechanism, where the inverse myotatic reflex is, again, a protective mechanism, but it's the opposite. It's going to shut the muscle down. And the name for this, for the other one, is reciprocal inhibition. This process is known as autogenic, A-U-T-O-G-E-N-I-C, inhibition. Autogenic means self-inhibition. So that agonist is going to be inhibited. Does that make sense? Okay, last one. Yay. Flexion withdrawal reflex. Same setup as before. The only difference here that you're going to see is this is my representation of a tack, like, or a pin. Let's say tack. Somebody tread on something sharp. Same basic setup. You have your neuronal cell body here. Okay, it's going to come in, come down, and bifurcate. Think about this one. So this kind. The tack is going to be felt as pain when you tread on it, and that is a nociceptor, N-O-C-I-C-E-P-T-O-R, a nociceptor. Nociceptor does nothing, it detects pain. Couple of things that are going to happen. Let's say this is the right leg. I didn't draw the left leg. But let's say you step on a tack with your right leg. What are you going to do? You're going to extend your knee, or you're going to flex your knee? Flex your knee. Correct. So let's go ahead and put in our interneurons. And where did I put that? There it is. So if I put my little interneurons, if I'm going to flex my knee, I'm going to activate my hamstrings and inhibit my quads, right? So I want an inhibitory neuron interacting with my alpha motor neuron for my quads, and I want a stimulatory neuron to pull away from that tack, interacting with the alpha motor neuron from the hamstrings. So this is alpha motor quads, and this one's going to be alpha motor hamstrings. So I want quads to be inhibited, and I want my hamstrings to be activated. Does that make sense? There's something else really cool that happens too. So, you step on a tack with your right foot and you go into knee flexion on the right to get away from the tack. So what has to happen on the left so I don't fall over? Extends. I have to extend it. If I flex it, I won't be able to stand up. So it's also called, so flexion withdrawal also has something called a crossed extension associated with it. So if one leg flexes, it makes sure that that information travels to both sides, and you get one flexion and the other extension. Okay, so again, just interacting through an inner neuron's connector neuron. One is going to be inhibitory. So let's keep it the same. So the one that I want to be activated, just stimulatory on the opposite side, is going to be my alpha motor neuron for my quads. Okay, and the one that's going to be inhibitory is going to be the alpha motor on the opposite side for my hamstrings. So I want my quads to be stimulated on the opposite side, and then I want my hamstrings to be inhibited. So it's really known as the flexion withdrawal cross extension reflex. Okay, good. Yes, Ben?
Could you please repeat what you said about the flexion and extension?
Sure. If I step on a tack with my right foot, I'm going to pull back. That's my knee flexion. Okay, so I'm going to activate that reflex. Is going to activate my hamstrings and inhibit my quads. But on the opposite side, I've got to get a signal saying I got to keep that leg extended so I don't fall over. Right?
Okay.
So when I get flexion on one side due to the withdrawal, due to the feeling of pain, it automatically causes extension of the contralateral side to help with postural balance.
Okay.
Does it make sense?
Yeah.
Yeah. Any other questions?